Welcome, deep divers. Have you ever been there, deep in a project, pushing like mad, only to feel like you're somehow making things worse?
Oh, absolutely. Or maybe you've seen a tiny issue, something you thought was isolated, just suddenly blow up.
Yeah, exactly. It creates chaos across the whole operation. It's that moment, isn't it? The sheer complexity of everything, especially in fields like construction, just feels, well, overwhelming.
hmm You get lost in the details, managing tasks, ticking boxes.
But the bigger picture, that whole web of connections that's really driving things, it just stays hidden. And that leads to frustration, mistakes, sometimes even, total failure.
It was a really common feeling, that sense of being stuck, reacting, constantly putting out fires, but never quite figuring out where the sparks are coming from or why they keep flaring up.
Right. And our usual project management approaches, they often encourage breaking things down, right?
Well, that
Linear steps.
they do, but the real power and often the source of our biggest headaches, it's not in those separate pieces.
hmm
It's in how they interact, how they influence each other, how they respond dynamically.
And that is precisely why we're doing this deep dive today. We're getting into thinking in systems. It's such a powerful framework for understanding and maybe even managing these complex challenges.
Yeah, it really is foundational.
Our main guide here is Donella Meadows' amazing book, Thinking in Systems, a primer. And this isn't just about learning definitions, okay? Think of this as maybe a shortcut to getting really informed. Finding those surprising facts, those aha moments that can genuinely change how you see things.
And our mission today, specifically for you listening, is to really shine a light on how a construction project, which seems linear, right? Design, bid, build,
Mm-hmm.
is actually a super complex dynamic system.
Uh-huh.
We're going to pull out the most important bits of insight from the sources we've looked at to give you a much more holistic way to understand and manage any project, big or small.
And here's what we hope you get out of this. By the end of our chat, you'll have this new lens, right? You'll start spotting those hidden connections, those subtle feedback loops you might have missed before.
And you'll see how small actions, if they're well placed, what Meadows calls leverage points, can actually lead to really significant positive changes.
Exactly. So let's stop just reacting and let's start really understanding. Let's unpack this. Okay, so first things first, let's start where Meadows does. What is a system? We hear the word all the time. Think of gears, maybe computers. But Meadows has a specific take, doesn't she? What's the key thing she emphasizes that maybe we often miss?
Yeah, I think the most crucial part, and it can be kind of surprising, is her insistence that a system is way more than just the sum of its parts. We tend to focus on the elements, right? The tangible things.
The components.
Exactly. But the big shift she asks us to make is to see that it's the organization, the relationships, the patterns of interaction between those components that really define the system. That's what gives it its unique properties, its ability to do something specific.
So it's not the bricks, it's how they're put together to make a wall or a building.
Precisely. It's about focusing on the invisible stuff. Really the connections, the information flows, and especially the feedback loops, not just the static pieces you can point to.
Okay, that focus on relationships and interactions, not just the bits and pieces, feels really important. And you mentioned feedback loops. These are critical, right? They're not just one-way signals.
Not at all. They're the dynamic engine. The output of an action feeds back and influences the next action. It creates these continuous cycles, cause and effect looping back on itself, constantly shaping how the system behaves over time.
Right, they make it dynamic, maybe even unpredictable sometimes.
Definitely. And to make it really concrete, think about a bicycle. You've got a pile of parts. Handlebars, wheels, frame, pedals, chain, just bits of metal and rubber. Those are the elements.
Okay.
But it's only when you arrange them just so, connect them with the chain, pinch in the cables, suddenly it's not just parts anymore, it's a bicycle. It achieves something transport that the parts alone could never do.
Yeah, okay, I get it. The arrangement, the connection is the system.
That's it. The interactivity, the relationships unlock the potential of the whole thing.
That bike analogy really helps. So now let's apply that to construction. We often think of projects as pretty linear, don't we? Design happens, then bidding, then construction starts. Step, step, step.
We absolutely do. It's a very common way to look at it.
But our sources are saying that this linear view, that's exactly where a lot of problems come from. Because it misunderstands the project as this dynamic, interconnected system we've been talking about.
It's a huge blind spot. And it persists, I think, because it feels simpler, more manageable on the surface. But it ignores the reality. Even the PMBOK guide, the Project Management Body of Knowledge, its latest edition, the 7th edition, show the big shift away from that traditional process view.
You mean the old ITTOs? Inputs, tools and techniques, outputs?
Exactly those. For years, that was the standard. And it gave structure, sure, but it often missed the dynamic interplay, the emergent stuff that happens on a real project.
So if the PMBOK is moving away from that, what's the new focus? How does it encourage this more systemic view?
The big change is from processes to principles and performance domains. The guide itself says this needs a different approach for thinking about the various aspects of project management. The emphasis now is squarely on delivering outcomes, regardless of the approach used.
Outcomes, not just process steps.
Right, which forces you, really, to think about the whole system and its purpose. What value are we delivering? How do all the pieces contribute to that? It's less about ticking boxes on a checklist.
That feels like a really fundamental shift, more holistic, and it introduces these performance domains. How do they fit into this systemic picture?
Yeah, the 8 domains, things like stakeholders, team, planning, delivery, uncertainty, measurement. They're described as related activities that are critical for the effective delivery of project outcomes.
Related activities. That word related seems key.
It is. It emphasizes interconnection. It moves away from thinking of these as separate silos you manage independently. You have to see how they constantly interact. Stakeholder needs influence planning, right? Uncertainty forces you to adapt your delivery approach. Measurement gives you feedback that loops back into all the other domains.
So it forces you to see the project as this single adaptive entity.
Exactly. Where a change in one area inevitably ripples through the others. It's about managing the whole interconnected system.
Okay, so projects are systems.
Yeah.
Complex, interconnected, dynamic. Got it. Now, the next big step is figuring out how these systems behave. Meadows gives us some really powerful tools for this, starting with these things called loops. Let's talk about reinforcing loops first. She calls them the engine of growth and decline. What makes them tick?
Right, reinforcing loops. We all intuitively get the idea of a vicious cycle, when things go bad and just keep getting worse.
Oh, yeah. Or sometimes a virtuous cycle when things go right.
Exactly. Meadows just gives us the formal language. A reinforcing loop is essentially positive feedback, but not positive as in good, positive as in amplifying. Whatever's happening, it makes more of it happen. Growth leads to faster growth. Decline leads to faster decline, exponentially.
Like compound interest. Or a snowball rolling downhill.
Perfect analogies. Or think of that awful screeching sound when a microphone gets too close to a speaker. A tiny sound gets amplified, fed back, amplified more. Boom. It spirals out of control fast. It's self-strengthening.
That sounds like a potent force, and maybe a dangerous one in construction. I can immediately think of that classic problem. The schedule slips.
Ah, yes, the schedule delay. This is where systems thinking gets really practical and often quite revealing. Let's walk through it. The schedule delay happens. Could be anything, right? Late materials, unexpected ground conditions, maybe slow approvals. We'll get back to that one.
Okay, so the project's behind. What's the immediate reaction?
Almost instinctive. Pressure. Right. Huge pressure. Make up time. Work faster. The team gets pushed to rush the next steps. Maybe work overtime. Maybe cut a few corners.
Yeah, that pressure is intense. And rushing detailed work in construction, what does that usually lead to?
It almost always leads to mistakes. Errors creep in, quality gets compromised, defects happen. You sacrifice thoroughness for speed, and something gives.
Okay, so now we have errors and defects, which means?
Rework. You have to fix the mistakes, replace the bad component, redo the inspection. And rework eats up more time and resources than doing it right the first time, usually significantly more.
Which, of course, makes the schedule even worse.
Bingo. You end up with further schedule delays, which puts more pressure on the team, leading to more rushing, more errors, more rework, and round it goes.
It's a perfect reinforcing loop, a vicious cycle, trapping the project.
Textbook example. And notice how our typical instinct, push harder, add more resources, crack the whip, can actually feed the loop. It makes the problem worse by accelerating the cycle of rushed work and errors.
So sometimes, counterintuitively, you might need to slow down certain parts to break the cycle. Or focus on quality first.
Precisely. Or, more fundamentally, address the root cause of the initial delay. Not just react to the symptom of being behind schedule. And it's not just the schedule, is it? This cycle hammers the budget. Rework costs money. Delays might incur penalties. And quality obviously suffers. Safety can even be compromised.
Yeah, it cascades everywhere. It becomes a much deeper problem than just a few lost days, trapped in decline.
Exactly. Pushing harder into that decline just digs the hole deeper. You have to understand the loop to break it.
Okay, so that's the power and the danger of reinforcing loops. What about the other kind Meadows talks about? Balancing loops, the forces of stability.
Right. Balancing loops are the system's brakes, or its thermostats. They work to counteract change and keep the system stable, or moving towards a specific goal or equilibrium. They resist runaway growth or decline. They provide stability.
Like a thermostat keeping the room temperature steady.
Perfect example. If it gets too hot, the AC kicks in, balancing action, to bring it back down to the set point, the goal. If it gets too cold, the heat comes on. It's constantly correcting deviations.
Okay, that makes sense. And we must have tons of these in construction, right? Projects are always fighting against things going off track.
Absolutely. Think about budget management. A core job for any construction manager or CM is tracking, projecting, and monitoring costs. Why? To keep the project within the budget.
Right, the budget is the goal.
Exactly. As the project progresses, estimates get replaced with actual committed amounts, plus cost estimates for any unknowns or contingencies. If the projected cost starts creeping above the budget, that deviation triggers action.
Like value engineering or scope adjustments or finding savings elsewhere.
Precisely. Those are the balancing actions. The loop works to pull the spending back towards the target. Without that loop, costs could just spiral upwards unchecked like a reinforcing loop of spending.
Okay, so budget control is a balancing loop. What about quality? Same idea.
Very much so. Quality management systems are designed as balancing loops. The CM monitors contractor compliance with the quality level expected. How? Through continuous reviews, inspections, testing, that's quality control, and through plant audits and process checks, quality assurance.
So if an inspection finds something wrong,
That information, the deviation from the quality standard, feeds back into the system. It triggers rework, or maybe a change in process, to correct the issue and bring the work back into compliance. It balances the pressure to cut corners or speed up against the need to meet the quality goal.
got it. And risk management, the PMBOK guide talks about a risk threshold, doesn't it? Sounds like another balancing mechanism.
It absolutely is. A risk threshold is defined as the measure of acceptable variation around an objective that reflects the risk appetite of the organization and stakeholders.
Yeah.
It's basically saying, how much risk are we willing to tolerate? That threshold acts as the goal for a balancing loop. If the project's assessed risk level starts to approach or exceed that threshold, it triggers risk response actions, maybe implementing mitigation plans, transferring risk, avoiding certain activities. The loop works to pull the project's risk exposure back down to an acceptable level. It keeps the project from drifting into territory the stakeholders deem too dangerous.
That's really clear. Balancing loops are about control, stability, hitting targets. But then Meadows brings in this other complicating factor, delays. She talks about the tyranny of delays and how they mess everything up, leading to unintended consequences.
This is where systems thinking really shows its power, because it goes beyond simple cause and effect. Delays are everywhere in systems. Information takes time to travel. Materials take time to arrive. Decisions take time to be made. It's natural.
Right. Nothing happens instantly.
But, Meadows points out, these delays can seriously distort how we perceive the system and how our actions affect it. We try to react, but because of the delay, our reaction might be based on old information, or it might hit the system at the wrong time. This can lead to outcomes that are not just unexpected, but actually the opposite of what we intended.
We think speeding things up will fix it, but the delay messes with that logic.
Exactly. Our intuition often tells us, react faster, fix it quicker. But the system's inherent delays can turn that speedy reaction into a source of instability.
Is there a good example of this, where trying to speed up makes things worse?
Meadows gives this brilliant classic example. The car dealer managing inventory. Imagine the dealer notices sales are picking up, and they're running low on cars. They want to react faster to avoid lost sales.
Makes sense.
Now, if they shorten their perception delay, how quickly they notice they're low on stock. Meadows shows it actually doesn't help much. It might even make the inventory levels bounce around a bit more, but it's not a big deal. But here's the kicker. If the dealer tries to shorten their reaction time, how quickly they order new cars from the factory to fill the gap they perceive, say, demanding delivery in 2 weeks instead of the usual 4 weeks, things get very much worse.
Worse? How?
The whole system starts oscillating wildly. They get huge overstocks followed by massive shortages. By trying to react faster than the system's natural rhythm allows, they amplify the fluctuations and create chaos. They overshoot, then undershoot, constantly chasing stability, but actually creating more instability.
Wow. So trying to fix the problem by reacting quicker actually destabilized the whole inventory system? That flies in the face of typical management thinking.
It really does. And that's the lesson. You have to understand and respect the inherent delays in the system. Trying to force it to respond faster than it can process information or materials can backfire spectacularly. It creates noise, oscillations, and instability.
Okay, so how does this tyranny of delays show up in construction? We definitely have delays there.
Oh, we have plenty. And a perfect, often painful example, highlighted in our sources, is managing submittals and approvals.
Hmm.
Shop drawings, material data, samples.
Yeah, the paper avalanche.
Exactly. Often, contracts have vague wording like, all submittals must be made immediately, or within a very short window after contract signing. So what do contractors do trying to avoid future delays or penalties?
They dump everything on the design team or CM right at the start.
Precisely. They send this landslide of submittals, often including stuff that isn't needed for months, just to cover themselves contractually. They're reacting to a perceived future threat by rushing an input now.
And that creates an immediate bottleneck for the reviewers, right?
Absolutely. It creates a huge perception delay for the field office. They waste critical time just sorting through the pile, trying to figure out which submittals are actually urgent and needed now versus which ones can wait.
Hmm.
The truly critical items get buried in the noise.
So the attempt to avoid future delay creates an immediate delay in processing what matters.
Exactly. And then there's the actual review time itself. Our sources say contractor review can take 1 to 5 days, sometimes longer. Things like reinforcing steel and structural steel shop drawings typically require the greatest amount of time. Even door schedules and hardware take significant time.
Okay.
So you have the initial landslide creating a sorting delay, then the inherent review time delays for complex items. These delays, caused partly by trying to rush things up front, can then ripple through the entire project schedule, holding up procurement, fabrication, and installation. It can actually cause the very schedule slips everyone was trying to avoid.
It's a perfect storm of delays, feeding delays, triggered by a poorly designed process and maybe flawed reactions.
It really is. Which is why the sources emphasize that a well-planned approach to scheduling submittals will ensure timely processing and better control. It's not just about batching work efficiently. It's about understanding the information flow as a system, respecting the time needed for review, and managing the timing of inputs to avoid overwhelming the system and creating these destabilizing delays. It might even mean redesigning the contract language or the collaboration process itself.
Okay, so understanding loops and delays is obviously vital. But it feels like a huge chunk of project problems, maybe even failures, comes from something simpler yet harder, just not seeing the whole system. Our sources state pretty clearly that many of our biggest project failures come from trying to solve problems without seeing the whole system. Why is it so hard for us to take that step back and see the entire picture?
It's a fundamental human challenge, isn't it? Meadows has a great concept for this: bounded rationality. What she means is that everyone in a system, every person, every department, every subcontractor makes decisions based on the information they have, the goals they have, the pressures they feel.
Their own little world, basically.
Exactly. Their rationality is bounded by their limited perspective. And the critical thing is, decisions that seem perfectly rational from that limited viewpoint may or may not lead to decisions that further the welfare of the system as a whole.
So what's good for the electrical sub might not be good for the overall project schedule or budget.
Precisely.
Yeah.
And if that's the case, Meadows argues, just swapping out the person or the subcontractor probably won't fix the underlying issue. If the system itself, its structure, its incentives, its information flows, encourages people to make locally optimal but globally suboptimal decisions, then redesigning the system is what's needed. It's often the system driving the behavior, not just individual bad apples.
That's a really important point. Stop blaming individuals and look at the structure.
Yeah.
So besides this bounded rationality, what other human tendencies trip us up when we try to think systemically?
Meadows points out a few other biases that make us inherently poor systems thinkers unless we're careful. We tend to misperceive risk. We worry excessively about some things, like plane crashes, while ignoring much bigger but less dramatic risks, like poor diet.
Yeah, we're not always rational about risk.
Not at all. We also tend to live in an exaggerated present. We focus heavily on recent events, the latest crisis, and often ignore long-term trends or historical patterns. We overreact to the now.
And we discount the future.
Hugely. We discount the future at rates that make no economic or ecological sense. We prioritize immediate gratification or short-term gains over long-term sustainability or consequences. Think about decisions around maintenance spending or environmental impacts. This short-term focus can be disastrous from a systems perspective.
So our own brains are kind of wired against seeing the big long-term picture unless we consciously work at it, which makes tools that force us to make our assumptions visible really valuable, right?
Absolutely. That's another strength of the systems thinking methodology. When you actually try to draw a diagram of a system, mapping out the stocks, flows, feedback loops, or even write equations to model it, you are forced to make your assumptions visible and to express them with rigor.
You can't hide fuzzy thinking in a diagram.
Exactly. Your model has to be complete and it has to add up and it has to be consistent. You can't just wave your hands. It prevents those slippery mental models we all have where our assumptions might subtly shift depending on who we're talking to or what point we're trying to make. It demands clarity and consistency.
It forces a shared understanding, or at least exposes where the disagreements really lie. That feels very different from, say, some approaches to design, maybe in architecture, where there's sometimes this idea of the single genius imposing a total vision.
It does contrast sharply. There's an interesting tension Stuart Brand explores in How Buildings Learn. He talks about how architecture often aims for permanence, this unchanging ideal structure. But the word building itself holds a dual meaning, doesn't it? It's both the action of building and the thing that is built.
Ah, so a building is always
Yep.
building, always changing.
In a sense, yes. Brand argues a building is always building and rebuilding. The reality of its existence is fluid, constantly adapting to use, weather, renovations. It's a verb as much as a noun.
Okay.
And he critiques the modern movement's embrace of the German idea of Gestalt totality, where some architects aimed for total control over every single detail, trying to freeze the building in a perfect, unchanging state. Brand says this desire for total control defies what should have been learned from the history of architecture courses.
Because buildings inevitably change and adapt over time.
Exactly. It's a rejection of the building as a dynamic, evolving system. It fails to account for how buildings interact with people, technology, and the environment over decades, even centuries.
So it's like trying to impose a static snapshot onto a moving film.
That's a great way to put it. Brand contrasts this with the buildings we often admire for their longevity and character, like the Gothic palazzos of Venice. He describes them as time-drenched, full of a kaleidoscope of periods and cultural styles all patched together in layers of mismatched fragments.
They show their history, their adaptations.
Precisely. They embody an organic, evolving system, not a static, master-planned object. They bear the marks of constant adaptation, repair, reuse. They show how the building itself learns and changes. It's a powerful lesson in designing for change, acknowledging the dynamism inherent in the built environment.
Okay, this is all fascinating, understanding the complexity, the loops, the delays, the need for a holistic view. But the big question is, how do we actually use this understanding? If systems are so complex, where do we intervene to make things better? Where do we push or pull?
This is where Donella Meadows gives us one of her most powerful and practical concepts, leverage points.
Leverage points sounds important.
It really is. She defines them as places within a complex system where a small change can lead to a large effect. It's about finding the sweet spot. Instead of applying huge effort everywhere or focusing only on the obvious symptoms, you look for those specific places where a small, targeted intervention can ripple through the system and create significant lasting change.
So it's about finding the system's acupuncture points, maybe, where a small needle has a big effect.
That's a fantastic analogy, yes. And crucially, she points out, these leverage points are often not obvious. They're frequently counterintuitive, hidden within the system's structure. Our normal problem-solving instincts might lead us elsewhere, usually to treating the symptoms.
Right. This connects really well with another concept, doesn't it? Eli Goldrat's theory of constraints from his book, The Goal. He talks about bottlenecks. Are bottlenecks a type of leverage point?
Absolutely. TOC is essentially a methodology for finding and managing the primary leverage point in a production system, which Goldrat identifies as the bottleneck or the constraint. The entire philosophy revolves around the idea that any complex system's output is ultimately limited by its single biggest constraint.
The slowest step in the process basically dictates the speed of the whole thing.
Exactly. And this leads to Goldrat's most famous and critical principle regarding bottlenecks. He states, very simply, An hour lost at a bottleneck is an hour lost for the entire system.
Okay, that makes intuitive sense. If the slowest part stops, the whole line stops eventually.
Right, because the bottleneck has no spare capacity anytime it's not running due to breakdown waiting for materials. Whatever that lost production capacity is lost forever for the entire system. You can't make it up elsewhere. It directly impacts the overall throughput. Every minute at the bottleneck is critical.
But then there's the flip side, the really counterintuitive part about non-bottlenecks. What was that again?
This is where TOC really messes with traditional efficiency thinking. Goldratt says an hour saved at a non-bottleneck is a mirage.
A mirage. How can saving time be a mirage? It sounds wrong.
It sounds totally wrong at first, but think about it systemically. A non-bottleneck, by definition, has extra capacity. It could work faster than the bottleneck. So if you make a non-bottleneck operation even faster, what happens?
It finishes its work sooner and then waits.
Exactly. It just creates more idle time for that non-bottleneck resource. It doesn't actually increase the amount of product coming out of the end of the entire system because the overall output is still governed by the speed of the bottleneck. So the time or money you thought you saved by optimizing the non-bottleneck, it's an illusion in terms of overall system performance.
Wow. Okay. So optimizing everything isn't the goal. Optimizing the constraint is the goal, and managing everything else around it.
Precisely. Focus your improvement efforts where they actually impact the system's output, the bottleneck. Don't waste resources making non-bottlenecks even faster if it doesn't help the constraint.
How does this play out practically? Goldratt uses examples like batch sizes, right? Making batches smaller seems inefficient.
Yeah, that's a classic goal example.
Hmm?
Cutting batch sizes in half means you double the number of times you have to do setups. Traditionally, that looks like adding cost and wasting time. More setups, bad, right?
Seems like it.
But if those extra setups happen at non-bottleneck machines
Mm.
and they utilize the idle time those machines already have, then it doesn't actually slow down the system. In fact, it can speed the whole thing up. Smaller batches mean work in progress flows through the system much faster. You reduce lead times, improve responsiveness, and can actually increase the overall throughput because materials aren't sitting around in huge piles waiting. You're using the non-bottleneck idle time strategically to improve the flow for the entire system.
Okay, that is a major shift in thinking. It's not about keeping every machine busy. It's about maximizing the flow through the constraint.
Exactly. It's a completely different paradigm. And Goldratt himself noted, in an interview included in later editions of The Goal, that people often resist these kinds of paradigm shifts.
Until they have to.
Pretty much. He said people typically only embrace TOC when three things happen. One, there's real pressure to improve. They're in a crisis or just can't meet demand. Two, it's obvious to them that there is no remedy within their existing paradigm. They've tried everything else based on traditional cost world thinking, and it hasn't worked. And three, something helps them take that first step. A book, a consultant, a workshop that shows them this different way of seeing things. It often takes a push.
So understanding leverage points, whether it's Meadows' broader concept or Goldratt's focus on bottlenecks, gives us a much smarter toolkit for project management, doesn't it?
A much smarter, more targeted toolkit. It's about being effective and insightful, finding where to apply pressure for maximum effect, rather than just working harder across the board.
And this isn't just theoretical. Our sources show this kind of thinking is being applied in things like lean construction research, specifically with the last planner system or LPS.
Yes, exactly. There's research actively looking for the high leverage drivers of LPS performance. They're trying to pinpoint the few actions or behaviors of the project team that are highly correlated with desired project outcomes, like meeting schedule and budget. It's a direct search for the leverage points within the LPS framework.
Okay, so what are some of these high leverage factors they're finding for LPS? What really moves the needle?
The research points to a few key underlying capabilities. First, having stable look-ahead schedules. This means a reliable, clear view of the work coming up, which allows teams to proactively spot and deal with potential roadblocks or constraints.
So predictability in the near term.
Right. Second, it's about requesting and obtaining reliable commitments to remove unresolved constraints. This is crucial. It's not just identifying roadblocks, but getting firm promises from the people responsible, whether it's for materials, information, or resources, and making sure those promises are actually kept. Reliability of commitments is key.
Holding people accountable for removing constraints.
Yes. And third, it's about developing and implementing countermeasures to prevent repeated plan failures. This is the learning loop. When a plan fails, don't just fix the immediate problem. Figure out why it failed and put systems or process changes in place so it doesn't happen again. closing that feedback loop on failure.
And they even suggest metrics to help teams focus on these specific high-leverage behaviors.
They do. Metrics like percent promises made and, more importantly, percent promises kept. These metrics shine a spotlight directly on the reliability of the commitments being made to clear constraints. It forces the team to focus on that crucial behavior follow-through, which is identified as a high leverage point for improving overall project predictability and performance. It's a great example of using metrics to drive focus towards systemic leverage points.
This is really pulling together now. We see the theory of systems thinking, the importance of loops, delays, leverage points, and now how it connects to practical tools like TOC and LPS. So let's look more broadly. Where else do we see systems thinking really showing up in modern construction best practices?
Well, one of the most prominent areas is definitely sustainable construction or green building. These projects, almost by definition, demand a much higher level of integration and systems thinking.
Because everything is so interconnected. Energy, water, materials, site.
Exactly. You can't optimize one system, like energy efficiency, without considering its impact on others, like indoor air quality or material selection. It forces an integrated design process.
Which means getting everyone involved much earlier and working together more closely than in traditional methods.
Precisely. It's not a linear handoff. The sources emphasize the need to orient all members of the project team to the goal and objectives for sustainability right from the start. This often involves team building in the form of group exercise to make sure everyone, architects, engineers, contractors, even the owner, understands the interconnected goals and how their piece fits into the larger puzzle.
It's actively fighting that bounded rationality by getting everyone to see the bigger system goals.
That's a great way to put it. And the contracts often reflect this too. We see more performance-based design contracts that provide financial incentives to implement certain sustainable design features.
Like rewarding the team for hitting energy targets.
Exactly. Or for designing systems that work together, like using natural ventilation and daylighting effectively, which then allows you to downsize the mechanical and electrical systems. That saves energy long-term, but also potentially reduces the initial capital cost. It's a win-win driven by integrated systemic thinking.
Okay, that makes sense for sustainability. What about technology? Building information modeling, BIM, feels inherently systemic, doesn't it? It's all about integrating information.
BIM is a prime example of technology enabling systems thinking in construction. The BIM handbook highlights the shift it allows, management of projects at the building object level rather than at a file level.
So instead of just lines on separate drawings, you have intelligent objects, walls, pipes, ducts that know what they are and how they relate to each other in a central model.
Exactly. A wall knows it's a wall, its material, its fire rating. And if you change that wall, the model can automatically update related elements like room areas or door schedules. It creates this integrated dynamic model of the project.
A single source of truth, hopefully.
That's the goal. And BIM repositories are key here, helping to manage the synchronization of multiple models representing a project, architectural, structural, MEP, etc. This integration drastically reduces the clashes and errors that come from working with fragmented, out-of-date information. Less rework, fewer delays directly addressing those system problems we talked about.
And clash detection is a big part of BIM's value, right? Finding where a pipe hits a beam before it happens on site.
Huge value. And the tools are getting more sophisticated, identifying not just hard clashes, two things in the same space, but also soft clashes, like not enough room for maintenance access.
Okay.
But the really powerful systemic part is the feedback loop. Technologies like the Open BIM Collaboration Format, BCF, allow feedback from clash detection back into the originating building model. So the issue identified in the coordination model can be directly communicated and tracked back in the architect's or engineer's design software.
So it's not just finding the clash, it's closing the loop to get it fixed efficiently at the source.
Exactly. It's a built-in feedback mechanism that improves the design systemically, preventing problems from ever reaching the field. That's a massive improvement over finding clashes during construction.
And BIM isn't just 3D, right? There's 4D, adding time.
Right. 4D modeling links the 3D BIM model to the project schedule data. This creates a dynamic visualization of the construction sequence over time. You can literally watch the building come together on screen.
What's the systemic benefit of that?
It allows teams to visualize the construction flow, identify potential bottlenecks in the sequence, plan logistics and site layout much more effectively, and spot time-based clashes like needing the same crane in two places at once. It brings the crucial dimension of time into the system model explicitly.
So, like with any powerful system, you need clear goals for using BIM. It's not magic on its own.
Definitely not. The Construction Management Association of America's standards stress that CMs need to work with owners early on to establish the goals and objectives of using BIM. What do you want to achieve with it? What's the scope? Who's responsible for what? Without that clarity, it can just become an expensive drafting tool instead of the powerful project integration system it can be.
Okay, so we see systems thinking in integrated design in BIM. How does this mindset help tackle those really big challenges facing the industry now, like sustainability in more detail and the massive supply chain disruptions we've seen?
Well, as we touched on, sustainable construction is a systemic response.
Mm.
It's the industry acknowledging it's part of a larger ecological system and needing to change its practices, moving away from just extracting resources and generating waste.
Mm.
It's a response to climate change, resource depletion, deforestation, all symptoms of unsustainable systems.
And a big part of that response is trying to create circular material loops, right? Moving away from the linear take, make, dispose model.
Precisely. It's about fundamentally redesigning the material flow system. The goals mentioned in our sources are examples of systemic targets, aiming for 35% recycled content, sourcing 67% of materials regionally, using 96% certified sustainable wood, recycling 89% of construction waste. Each of these targets is an intervention aimed at making the material system more circular and less impactful.
And this even applies to the end of a building's life. Deconstruction instead of demolition.
Yes, that's a perfect example of changing a system's boundary condition. Demolition treats the building as waste at the end. Deconstruction sees it as a source of valuable materials, carefully salvaging things like boards and lumber, decorative trim, hardware, light fixtures, windows and doors. Not only keeps them at a landfill, but creates a supply stream for reuse, sometimes at a premium. It turns waste into a resource, closing the loop.
And supply chains. After the chaos of the last few years, how does systems thinking help there? PMI flags disruption as a major challenge.
Systems thinking is crucial for building supply chain resilience. Instead of just reacting when a port shuts down or a supplier fails, you look at the entire network. You map dependencies, identify critical single points of failure, understand the feedback loops, how a delay in one place ripples through.
So you can be more proactive.
Exactly. You might diversify suppliers, even if it costs a bit more, to reduce reliance on one source. You might hold strategic inventory buffers at key points. You might build closer relationships with suppliers to improve information flow. It's about understanding the interconnections and designing a system that can better absorb shocks, rather than just optimizing for the lowest costs under stable conditions, which we now know are not guaranteed.
It's really powerful seeing how systems thinking applies to modern challenges and practices, but it makes me wonder, is this a totally new idea? Or can we see glimpses of this kind of thinking, maybe intuitively, looking back through architectural history?
That's a great question. And you definitely can find examples where people seem to intuitively grasp systemic principles even thousands of years ago. Take Vitruvius, the Roman architect. His book, The 10 Books on Architecture, has some amazing insights.
Vitruvius, what did he say that sounds like systems thinking?
He gave very specific instructions about foundations. He said pilings shouldn't just be under the outside walls, but also under those which divide the fabric, the interior walls too. Why? Because, he reasoned, if the inner foundations are different, the nude walls will think, and the outside ones will remain unmoved.
And the whole thing would crack apart.
Exactly. He said it will occasion all the walls to open and ruin the whole edifice. That's a crystal clear recognition of structural interdependence. He saw the building as a system where the foundation strategy had to be consistent across all connected parts to ensure the stability of the whole. A failure in one part brings down the system.
Amazing. So even without the modern jargon, he understood the systemic connection. What about later periods, like the Gothic cathedrals? They feel very integrated.
They absolutely do. Think about Abbot Sugar's design for the choir of St. Denis in the 12th century, often seen as the birthplace of Gothic. It had a double ambulatory with radiating chapels where the outer ambulatory and the chapels actually merge. It created this incredibly unified, flowing space.
Not just separate boxes connected by a corridor.
Right. And the systemic brilliance was how this structure served another purpose. Light. The radial alignment of the piers and columns from a single center makes it possible to bring exterior light to the apse unobstructed. Sugar himself described how the whole sanctuary was pervaded by a wonderful and continuous light.
So the structure and the light were designed as one integrated system.
Precisely. The structural system enabled the light system, which in turn defined the spiritual experience of the space. Form, structure, light, and purpose were all deeply interconnected, a truly integrated system design.
That's beautiful. What about cities? Urban planning must involve systems thinking or suffer when it doesn't.
Definitely. And sometimes the lack of systemic integration has long-lasting effects. Our sources mention Cairo, where there was a pattern of conquerors building their new headquarters outside the existing urban boundary. This repeatedly isolated the ruling class.
How did that affect the city's growth systemically?
It led to a different pattern of expansion compared to the typical Western model, the Borg-Faubourg model, where suburbs outside the walls, Faubourgs, would eventually get absorbed into the main city, Burg, integrating economically and administratively.
But in Cairo, they stayed separate.
Largely, yes. The repeated decision to build separate power centers outside the existing core led to a more fragmented urban growth, with distinct, often disconnected nodes, rather than an organically expanding integrated core. It shows how initial decisions, driven by the ruler's bounded rationality perhaps, set up different long-term systemic dynamics for urban evolution.
Fascinating. Different feedback loops shaping the city's form.
Okay, jumping ahead, what about the famous modernist slogan, "Form ever follows function"? That sounds pretty systemic. It absolutely does. Louis Sullivan's phrase from 1896 became a founding idea of modernist architecture. It asserts a direct causal link, a systemic relationship between the purpose of a building, its function, and its resulting shape, its form. It's a call for integration, rejecting arbitrary style in favor of designs driven by the building's operational system.
And then there was the Crystal Palace, a total revolution in how buildings were made, right? A system of construction.
Completely. Built for the Great Exhibition in 1851, it was astonishing. It wasn't built traditionally. It was assembled using prefabricated parts, standardized modules of iron and glass, accurately bolted together on site, incredibly quickly.
Industrial production applied to building.
Yes, it demonstrated a whole new system of design, manufacturing, and assembly. Contemporaries saw it immediately, predicting it would be a revolution in architecture. It was a system of standardized, interconnected components, prefiguring so much of modern construction.
And finally, someone like Frank Lloyd Wright. His organic architecture seems very focused on integration with the environment.
Very much so. Wright was deeply influenced by Japanese architectural principles, emphasizing the connection between nature and architecture. He didn't see the building as separate from its site. He aimed for an organic integration, where the building grew out of the landscape, forming a coherent system with its surroundings.
Part of the larger natural system.
Exactly. He talked about individual integrity in art and designing organically, free from rigid styles, allowing the building's form to resonate with its environment and purpose. It was a vision of a holistic, integrated system building, site, inhabitants, all working together. Hashtag tag outro.
Wow. This has been such an illuminating journey. We've really dug into how looking through the lens of systems thinking can fundamentally change how we see projects, buildings, even history, from understanding the basic idea of a system.
To decoding those complex behaviors, the reinforcing loops that drive growth or decay, the balancing loops that seek stability, and those tricky counterintuitive delays that cause so many unintended consequences.
Yeah, and realizing the dangers of just looking at parts in isolation because of our own bounded rationality and biases, and then finding the power in Meadows' idea of leverage points.
And Goldratt's focus on bottlenecks, knowing where to intervene for the biggest impact instead of just flailing around.
It really feels like systems thinking helps us get beneath the surface, doesn't it? To see the underlying structures and dynamics that are really driving what happens on a project.
Absolutely. It lets us see the whole forest, not just the individual trees, and crucially understand how the health of the forest affects every single tree within it.
And it's not just theory. We've seen how this mindset is a core part of modern best practices, integrated design for sustainability, the power of BIM, tackling huge issues like supply chain resilience. It really is a foundational skill for managing complexity today.
It truly empowers you, the listener, with a more holistic, more effective way to approach any complex challenge, to find real solutions that stick, not just Band-Aids that might cause other problems down the line.
So the invitation to you is, take this lens. Apply it to your own work, your own projects. Start asking questions. What are the key relationships here? What loops are driving the behavior I'm seeing? Where are the delays and what impact are they having?
And most importantly, Where are the leverage points? Where could a small, smart change make a really big difference? Don't just treat the symptoms. Look for ways to influence the underlying system structure.
And we'll leave you with a final thought to chew on, building on that idea from Stuart Brand. If we accept that a building is always building and rebuilding, that it's a dynamic process, a verb, not just a static noun, what hidden or forgotten relationships in your own projects, maybe even in your own team or organization, might be waiting to be seen differently, waiting to be retuned, or perhaps even completely redesigned if you only take the time to look at the whole dynamic system.
That's a great question to ponder. Thanks for joining us on this deep dive.
Until next time, keep digging, keep learning, and keep thinking in systems.